Now in question number 12, it says for polytropic process PV raised to power n is equal to constant, molar heat capacity of an ideal gas is given by. Now we need to understand that from the first law of thermodynamics, which is essentially conservation of energy, we have dq is equal to du minus dw. Now remember that polytropic process is very different from adiabatic process. In adiabatic process, we have PV raised to power gamma is equal to constant, where exponent is Poisson's ratio. And this was practically derived from the condition that delta Q is equal to 0. However, when we say polytropic process, this exponent is something apart from gamma, and therefore in this polytropic process having the equation PV raised to power n is equal to constant, where n is not equal to gamma, we cannot say delta Q is equal to 0. We cannot say, right? And therefore delta Q will have a finite value, so it's not going to go to 0. So let us say for the overall process, the molar heat capacity is C, so dq will be equal to nc dt. It is neither Cp nor Cv because we don't know what kind of process is that, because pressure and volume both are changing. So it is nc dt, where C is the molar heat capacity that we have to find. Du is the change in internal energy, which anyways is given as ncv dt. Work done is minus pdv. So if we were to put the value over here, let's say for expansion, so it will be minus pdv, so it becomes plus. So molar heat capacity C would be equal to Cv plus pdv upon ndt. Now the process is polytropic in nature, which means it is given PV raised to power n is equal to constant. This is equation number 1. Also it is an ideal gas, so P is equal to nRT upon V. So equating 1 and 2 we get this relation, and rearranging we get this relation. This is important because for finding the molar heat capacity we have to find dV by dt terms. This is what we will get by differentiating this expression number 3. So if we differentiate, so k into 1 minus n v raised to power 1 minus n minus 1 dV is equal to nr dt. On rearranging we get this, and this expression we can see from this equation that nr v raised to power n upon k is v by t. So this essentially becomes v by t into bracket 1 minus n. So now if we were to put the value right for C, so it will be equal to Cv plus, this is P times P by n times dV by dt, which we know as v upon t times 1 minus n, right? So this PV upon nt is nothing but equal to R. Therefore for this question we can say molar heat capacity would be Cv plus R upon 1 minus n, right? So for question number 12 we can see that it is equal to option number B. Hence for this question option number B is correct.